Hello and welcome to this Foundations of College Chemistry lecture for Chapter 6. I will be reviewing a little bit from 3.3. We've already went over that, but I want to refresh your mind about counting molecules, counting atoms and molecules. But this is mainly going to focus on naming and formula writing of inorganic compounds. All right, let's get into it. So, like I said, I'm just going to briefly go over molecular versus ionic compounds, how to write formulas, and composition of compounds from 3.3. Now, I did not test heavily on this on the unit test, but I will be putting a lot of this from this particular section onto your unit test for Chapter 6. And then for Chapter 6, this is your chapter outline. Okay. All right, now these videos will be part of your FOCC in-class homework, so I'll make sure that those are attached to that study guide. Make sure you watch them. I've broken them down to each individual kind of naming and formula writing. So this one is strictly molecular compounds, and then everything else is ionic or acids. All right, so let's briefly go over 3.3. So a compound is a substance that contains two different elements that are chemically combined. These compounds can decompose into their elemental form and be able to rearrange themselves into different substances in a chemical reaction, shown here on the PowerPoint. Now, there's two main differences between molecular and ionic compounds. Molecular are strictly two nonmetals, so they can be any form of two nonmetals. Here you've got water, H2O, but H2O2 is hydrogen peroxide. So you have this law of multiple and definite proportions that you have to remember, okay? But molecular is two nonmetals, a compound that has no charge to it, okay, no ions. An ionic compound is always going to have a metal. The metal always goes first in the formula or the name. And it forms ions when it decomposes into its elemental forms, as shown here with salt. Sodium has a positive charge and chlorine has a negative charge. Another main difference is that when you're dealing with molecular compounds, they are held together by covalent bonds where they share valence electrons. They're not transferring valence electrons like you see in ionics. So with molecular, you have the sharing of the valence electrons. In ionic, you have the complete transfer of the valence electrons, which then gives you ions, positive and negative ions. Now, molecules are the smallest uncharged individual unit of a compound, typically of a molecular compound. A molecule cannot be further divided without destroying its identity. So what that means is that water is a molecule. It's a molecular compound that's a molecule. If we break that down into its elemental form, then we're changing its identity. It's no longer water, it's hydrogen gas with oxygen gas that have completely different properties from water. Ions are charged atoms or groups of atoms. So the positive charged ion is a cation, and the negatively charged ion is an anion. There are a lot of different compounds, and this is where we get into the law of multiple proportions, where you can have the same two nonmetals that are bonding together, but make completely different compounds. So here's the property of water and the property of hydrogen peroxide. But it's still hydrogen and oxygen bonding. Here, where we're getting into sulfuric acid, we're actually counting atoms. So this is one possible formula is HHS and then 4 oxygens. The better formula is we put the H's together and the SO4, so it's H2SO4. So how do we write formulas of any compound, whether it's molecular or ionic? Well, you have the elemental symbol that has to be written just as it is on the periodic table. So you're going to capitalize or lowercase. So like iron is capital F with a lowercase e. So you got to write the symbol of the element the way it's on the periodic table. Okay. Then the formula will contain one atom of an element. If that's the case, we do not put a subscript of 1. It's redundant. The symbol, the elemental symbol itself means 1. So here, like, you've got 2 hydrogens being shown in this formula, but only 1 sulfur. So it's not H2S1O4. It's redundant to put the 1. Now, when a formula contains more than 1 atom of an element, the number is indicated by the subscript, as you can see in the red. If we have parentheses with something, this typically shows that it's definitely an ionic compound and that it's not bonded to just a nonmetal. It's bonded to what's called a polyatomic ion, which is typically 2 nonmetals that are bonded but have a charge and do form a negative or positive ion. So here on the screen we have calcium bonded to nitrate, and nitrate by itself has a -1 charge. Well, calcium is in group 2, which is the alkali metals. So when calcium gives up its electrons, it can give up 2 electrons, valence electrons. So it takes 2 of those nitrates, 2 of the whole thing, to balance out that chemical compound. All elements in compounds are chemically neutral. They want to be neutral. So when writing formulas, we've got to deal with charges of individual elements, especially with ionic compounds. So let's practice this. How many of each element is present in K3PO4? Well, we've got Kp and O. We look at the subscripts. There's a 3 by the K, so that's 3 K atoms. There's no subscript by the phosphorus, the P, so that means 1. And there's a subscript by the 4, or by the oxygen, which means there's 4 O atoms. Now, how many of each element is present in MgOH with the parentheses 2? Well, we got magnesium, we got oxygen, and we got hydrogen. So when we have parentheses around something, you have to distribute that number outside the parentheses to everything inside the parentheses. So that 2 is going to apply to the oxygen and hydrogen, which, since there's no subscript by magnesium, that means there's only 1 magnesium. But because there is a 2 outside the parentheses, then there are 2 oxygen atoms and 2 hydrogen atoms. So, how would you read the following formulas aloud? Now, I want to caution you here. There are several different naming systems. It depends on what chemistry class you're in. The 2 basic ones are inorganic and organic. But within organic, you have biochemistry, which typically has a number slash or a number and a dash and then a chemical name. I want to caution you, you need to learn nomenclature of inorganic formulas. You need to follow the rules and the flow chart that I'm going to provide for you. So let me show you the flow chart that I'm talking about. And I will print this out and give this to you to do your homework and the in-class work when we get in class. So this side is, we want to name the compound. All right, so we have a formula and we want to go to the name. So now I can't print these out in color. So in class I'll have like 2 different color highlighters and we'll highlight the boxes. And it actually goes yes, no questions all the way down. So you just got to follow the flow chart. All right. So on the previous slide we have these formulas and we want to go to a name. So let's look at this first one. Does the compound contain a metal, hydrogen first, or a polyatomic ion? Well, there's no polyatomic ion because I only see 2 elements. Sodium, Na, is a metal. So we go to the blue side. Yes, ionic naming system. This can have 2 or more elements. And then does the positive ion have only 1 possible charge? Well, Group 1, Group 2, and Group 3, like aluminum, gallium, and all those, do have only a single charge. But the transition metals in the center have multiple charges. So if you have a transition metal, now we got to do another step. That's why there's 2 columns here of blue. In the transition metals, there are only 2 metals that have a single charge, and that's zinc and silver. So sodium is in group 1, so it only has 1 positive charge. So we go yes. And then it says name the positive ion, name the negative ion with an ending of IED. Or if it's 1 positive ion metal with a polyatomic, you would use the polyatomic name. So you would put the name of the metal and then the polyatomic name. So let's go back. This is sodium, this is chlorine, so it would be sodium chloride. And that's how we're going to read the flowchart formula to name. And we'll do a lot of practice of this in class. So we got magnesium and oxygen. That's a single metal to a nonmetal, so magnesium oxide. We have barium, and then this is a polyatomic ion. You will not have to memorize the polyatomic ions. You will be given the ion chart. So you just got to find NO3, which is nitrate, so you put the name. So it would be barium nitrate. Now, C2H6O. This is 3 elements. So this is not an well, it has a chemical name, but it's not inorganic. With that extra oxygen there, we would have to rely on organic naming, which is not something you're required to learn. So this was kind of thrown in there to trip you up. Okay. All right, so composition of compounds. This is, we kind of got into this a little bit. Law of definite composition states that the compound always contains 2 or more elements chemically combined by definite proportions by mass. So we would find the total mass of water, which is 18.02, and then we take the 2 hydrogens, take its mass, divide by the whole, and times by 100. That's all you're doing here. Taking the part of each elemental mass and dividing by the whole mass, and then timesing it by 100. Now, law of multiple proportions, all that is you can have the same 2 elements bonding together, but in different ratios. You don't have to memorize this, but there are like a lot of what we call hydrocarbons, which is just carbon and hydrogen. So here it gives you 2 examples, but there's methane, there's octane, there's ethane, there's propane. All of them are different combinations of carbon and hydrogen. That's all what law of multiple proportions is. All right, let's get into chapter 6. So chemical nomenclature is a systematic way of naming compounds that can be used universally. Typically, the rules for naming compounds come from the IUPAC. That's the International System of Chemistry that formulates a chemical name that everyone is going to recognize. So it's kind of like the metric system. All right, it's very easy to follow. There are guidelines and rules to help you learn the system, and it's used universally. Okay. Common names can be arbitrary. They can, like laughing gas, all right? That's nitrous oxide. We want to not deal with common names. We want to deal with the inorganic chemical name, okay? So the systematic name for nitrous oxide, laughing gas, is dinitrogen monoxide. That's what you want to learn. So like I said, I want to caution you. I want you to follow the flow chart that I give you, not just look up answers on the internet, because you're not going to know, is this the true inorganic name, or is this the common name, or is this the organic naming system? It's just better for you to learn from the flow chart and just follow that. Okay? All right. So, nomenclature, here's an example of CaO. Calcium oxide. That common name is lime. Calcium carbonate, when you add carbon and more oxygen to it, you get limestone. So there's always going to be common names that you can easily look up, but we want the systematic name. Now, this flowchart is in your book. It's okay. I don't mind this flowchart, but I want you to actually follow this one. One side is formula to name, and then the other side is name to formula. And again, I can't print out in color, but we'll highlight it, and it covers everything that you need to know if you have the name and you want to go to the formula. Now, elements and ions. So, there are 7 diatomic molecules that you need to know. This is going to be very important when we get to Chapter 7, stoichiometry. And if you look on the periodic table, it's hydrogen over to nitrogen, and nitrogen to fluorine spells out NOF, and then it's all the halogens. So hydrogen, NOF, halogens. And it actually makes a nice little 7 on the periodic table. Now, there are 2 other elements that exist, what we call in polyatomic arrangements. S8, sulfur. So when sulfur, it typically will bond with other things, but if it's by itself, it tends to bond with 8 atoms of sulfur and kind of not make a crystal, but it's a polyatomic arrangement to where it's not just by itself. Phosphorus is the other one. It typically makes P4. Ions are where we're changing the number of electrons. So like I said before, every element and compound want to be chemically neutral. So a neutral potassium ion here on the slide is 19 protons and 19 electrons. Right? Potassium has an atomic number of 19. So the atomic number tells you protons and electrons. But if it becomes an ion, it gains or loses valence electrons, then we're changing the number of electrons, and it will either become positive or negative. So this goes for metals and nonmetals. This one happens to show the example of potassium, that it actually can transfer 1 valence electron when it bonds, so it becomes more positive than negative, and it's a cation. Any neutral atom that loses an electron is a cation. So magnesium in group 2, the alkaline metals, can lose up to 2. Aluminum and the metals in group 3, which is under boron, we got aluminum, we got gallium, indium, and thallium. They can lose up to 3 electrons, so they have a positive 3 charge. So again, you don't have to memorize all the ions or polyatomic ions. You'll have an ion sheet. Anions gain electrons, so they become more negative. They're getting more electrons than protons. So here's the example of oxygen, and it gains 2 electrons. I also want you to notice how when they gain electrons, they slightly become larger. If you look at the neutral chlorine atom versus the ion chlorine atom. If I go back to the metal, the cation, where it loses electrons, it gets smaller. So that outer shell shrinks in because now we got more protons pulling on the negative electrons, so it makes the atom smaller. Here's a chart that's in your book. It just goes through most of the common nonmetals that are bonded to metals. And notice the root word is there, and it ends in IED. This is just practice on how many letters you got to drop. The halogens are fluorine, bromine, iodine, and chlorine. You're changing the N to a D, okay? Where with oxygen and nitrogen, you have to drop the GEN, okay? So it's just going to take practice. Now, this is close to the ion chart you're going to get. Notice how, and your ion chart will give you some of the transition metals. On your test, you will get a ion chart, and if I add any other transition metal on there, I will add it to the ion chart and give you that one. but you don't have to memorize the charges. But you do need this to do your homework. All right, here is writing formulas and names of ionic compounds. This is just a chart here. It's showing you how the sum of the charges always have to equal 0. So here's the rules for writing formulas from names. So pause the video if you need to take these steps. Again, like I said, we're going to cover this in class and go over a lot of practice in class. Here's an example. So you write the symbol, put the charge above the symbol or to the side, and then you determine what you need to do in order to get that neutral, to get it to 0. Now, what's being shown on the slide is what I call the algebraic way, okay, where you find the common multiple between 2 and 3, all right? If this makes sense to you, then I want you to do it this way. However, I teach it a different way. I teach it by what's called the crisscross method. And I have another PowerPoint here. This is just molecular, but I have a PowerPoint that's going to go over ionic compounds, and I'm going to show that to you in class. But I do what's called the crisscross method. So if that makes more sense to you, then use that method. So pause the video, see if you can figure this out. We got magnesium oxide. Find the charges for each and see if you can pick the right formula. All right, so the answer is MgO. Magnesium is positive 2 and oxygen is negative 2. So when you add them up, they already equal 0. So we just write the symbols. Now, writing formulas from names of ionic compounds. Here's the solution for magnesium oxide. Now, naming binary compounds. They only contain 2 different elements. Binary compounds can be ionic or molecular. Ionic binary compounds can further be subdivided into a metal with 1 cation or a metal that can form multiple ions. And both of those can either be bonded to a single nonmetal or to a polyatomic ion. Here's some examples of how to write nonmetals again with the IED ending. And these are the rules. Again, this will be on your flowchart. Here's like kind of examples and the rules. And then here's some practice. So writing formulas for ionic compounds. So we got Al2O3. So we know that Al is aluminum and O is oxygen, which would become oxide. All you have to determine here is, do I need the Roman numeral like in A and D? Well, aluminum only has 1 single charge. So the correct answer is C. And then here is the solution for it. All right, here's another practice with calcium and sulfur. Now, metals containing multiple charges. When we're looking at the transition metals, because the transition metals can have multiple charges, we have to signify, are we reacting and bonding to copper 1 or copper 2, or iron 2 or iron 3, or chromium 2 or chromium 3. Like I said, every single transition metal has multiple charges except for the silver and the zinc. However, you're not going to have to know every single element in the transition metal with multiple charges. If I put something that is on my test that is not on the ion chart, I will put it on the ion chart and copy that off and give that to you for the test. You will not be using your own ion chart or periodic table. So here's some classic names. I do not want you to be using these. I want you to use copper 1 or copper 2 or iron 2 or iron 3. I don't want you to be using cuprous, cupric, ferrous, ferric, stannous, stannic. This is more, I would say, organic. Chem 151, 152. You would need to know these. I want you to write tin 2 or tin 4. Okay? Now, If you have a metal with multiple charges, how do you write it out? Well, again, this will be on your flow chart, but pause the video if you need to write the steps. So let's practice. We have to name the compound. Well, chromium is a multi-charged metal. You've got chromium and chlorine, so you know it's chromium chloride, but is it chromium chloride in A, D, or with Roman numerals? Well, you got to figure out the charges. You're kind of working reversely. You got to find out the total charge on the nonmetal, and because there's only one chromium, that chromium has to balance out, and that charge added up with the 3 chlorines has to equal 0. So pause the video and see if you can figure it out. All right, so correct answer was C. Chlorine has a -1 charge, and there's 3 of them, so that makes overall -3, so you need a +3 chromium. And here's the steps on how to figure that out. Now, copper 1 oxide means that copper has a +1 charge, but oxygen is a -2. So how many coppers do I need to cancel out that -2? I need +2, so I need 2 copper atoms to 1 oxygen to get to 0. Here is tin 4 fluoride. That means tin has a +4 charge. There's only 1 tin, so how many fluorines do I need to get to 0? I need 4, because 4 times -1 is -4. So it would be SnF4. Now, rules for naming molecular compounds. This is totally different from ionic. You do need to know these prefixes, right? I'm not sure if those are on the ion chart. All right, so think of mathematics. Triangle, triangle is 3. Pentagon, penta is 5. Hexagon, hexa is 6. Octagon, octa is 8. Mono is 1. Dice, you normally only have 2 dice in a game. Right? Just try to think of something that will help you remember the prefixes. And it's really simple. The rules for it is write the name of the first element, include the appropriate prefix. If the first element has more than 1, it gets a prefix. If it doesn't have more than 1 in the formula, then it's just the name of the compound. And the second element always, always, always gets a prefix, and it always, always gets the IED ending. So here we got P2O5, phosphorus and oxygen. There's 2 phosphorus, so that's more than 1, and there's 5 oxygens. So it's diphosphorus pentoxide. Okay? So the second element always, always gets the prefix and always gets the IED ending. And it says, name the following compound. This I would never give you, okay? This is an organic name. How would you even know that that is carbon and chlorine? So do not write this down. This is the book's PowerPoint. I don't modify these. They're copyrighted, so do not write this down. All right, so let's practice. You know it's S, that's sulfur. O is oxygen. You got 1 sulfur and 2 oxygens. So which one is the correct answer? If you answered A, you're on track. There's not more than 1 sulfur, so we do not put a prefix, so it's just the name of the first element. And the second element always, always gets a prefix and IED ending. So 2 means di, so dioxide. So what about acids? Acids, you've got to put hydro followed by the root of the second element and add it to it. And then you always add the word acid. Now, there are a couple of different ways of doing acids. This is kind of the rules. If it is hydrogen bonded to 1 single nonmetal. If it's bonded to a polyatomic ion, then there's different rules. So H to Cl, H to F, H to Br. Hydrogen to 1 single nonmetal has these rules. You put hydro, the root of the hydro is to represent the hydrogen, and then the root word of the second element with the ic suffix, and then add acid. So H2S is hydrosulfuric acid. Name HI, hydroiodic acid. H2SE, hydroselenic acid. HF, hydrofluoric acid. Now you might be wondering, wait a minute, why is sulfuric? Because that's a typo. Again, I don't modify these. It's hydrosulfuric, that U and R should not be there. Okay? So, yeah. Review the compound naming with moleculars. Always has an IED ending on the second element. You use prefixes if there's more than one on the first element, but always on the second element. Let me get my mouse out of the way here. So, here's some rules, and again, you'll have the flow chart to do your homework and to do the in-class work. And 6.5, using polyatomic ions. So again, on the ion chart, you don't have to memorize the names, but if you have a metal to a polyatomic, it's just put the name of the metal and the name of the polyatomic ion. Here are the common polyatomic ions that will be on your sheet. Oxyions, those are polyatomic ions that have oxygen in them. So like sulfate, phosphate, sulfite, phosphite, peridotite, they all have a specialized name. So just remember that anything that has oxygen in it is an oxyanion polyatomic. So here's some common ones. And more complicated polyatomic ions are like sodium hydrogen carbonate. Well, it's also called sodium bicarbonate. So on your ion chart, just go by what HCO3 that name is. If it says hydrogen carbonate, then you put that. If it's got bicarbonate, then you put that name. Now, oxyacids. Oxyacids are the ones that have the oxygen in it. So these are the 8s and ites on the polyatomic list. So you have hydrogen bonded to phosphate. We don't put hydrophosphoric acid. We just use the polyatomic name, and if it ends in 8, we put an ic at the end with the word acid. If it ends in ite, you put us. If it has an ic, then you also put us. So this we're just going to have to practice in class. Okay? Here's kind of a acids flow chart. I'm not going to be handing out an acids flow chart because I don't test on them a lot. That's more 151 and 152. There will be 1 or 2 on the test, and I think there is 1 on the final. Okay? And the most common ones is like phosphoric acid, sulfuric acid, I think cyanidic acid, that's hydrogen bonded to CN. And here's your learning objectives for Chapter 6. And I will see you in class.